All right. So welcome everyone. Today we are going to hear about mirror symmetry and algebro-geometric approach from Hülya Argüz. She's joining us from Université de Versailles from Paris-Saclay.
Thank you very much. Many thanks for the kind invitation. I appreciate being here together with all of you. What I'm going to talk about today is about mirror symmetry, and I'm going to talk about an algebro-geometric approach, which is based on the work of Gross and Siebert. So it's in the framework of the Gross-Siebert program in mirror symmetry. I shall say that I prepared a talk of colloquium style for a broad general audience, and I will not dig too much into details. But if you would like to interrupt me at any point, and if you may have if you may have any questions, please very welcome to ask them anytime. So what I'd like to talk about today is about mirror symmetry, what it is, and afterwards I will tell you about the main techniques we are using to understand mirror symmetry from this algebraic point of view of Gross-Siebert, namely Toric geometry, log geometry, and wall crossing algorithms. And at that, I will report on the recent advances in this framework and what we have done here. Okay, so what is mirror symmetry? Mirror symmetry is a phenomenon that came out of string theory, and string dualities and string theory propose that there should be mirror Calabi Yau manifolds. So these Calabi Yau manifolds arise because, string theory proposes that our universe is 10-dimensional, and it is obtained as a compactification of the usual 4-dimensional space-time with a Calabi Yau space, which is 6-dimensional. So this is in the framework of T-duality in string theory. There are also other theories like M theory and other branches of string theory where you might be interested in other Calabi Yau manifolds, which might not be where you might be interested in other spaces which might not be Calabi Yau or 6-dimensional. But this is one of the most influential frameworks, and in this theory, we are looking at Calabi Yau manifolds, which are of 6-dimensional, and I'm having just a slight trouble here not seeing what I'm typing because I constantly have popped up things to admit people. I don't know how to avoid this. Sorry about this. So the expectation in string theory is that these Calabi Yau manifolds, which are compactifying our space-time, arise as mirror pairs. They don't come as a single Calabi Yau, but if the laws of physics hold in one Calabi Yau, there is expected to be a mirror to it, which the laws of physics hold there as well. And the mathematical point of view is about investigating conjectural relationships between these mirror pairs of Calabi Yau manifolds. So from this point of view, mathematicians try to understand mirror symmetry to understand these conjectural relationships. And these are relationships between the two sides of mirror symmetry. On one side, X is a symplectic manifold with a symplectic structure. And on the other side, the mirror is expected to have a complex structure. And in the physics language, these sides are called A model and B model. A model is the symplectic side and B is the complex one. And the two most influential and important conjectures in this framework are phrased by Conjectural and Strominger-Yau-Zasov. So in this framework of mirror symmetry, the reason why mathematicians were a priori interested in this is due to the fact that physicists compute some invariants, and mirror symmetry provided a tool a priori to obtain Gromov-Witten invariants of Calabi Yau manifolds by using these mirror symmetric predictions. the dualities essentially. And however, apart from being useful for enumerative predictions, Conjecture taught that there should be a deeper relationship between mirror manifolds, not only for enumerative invariance, but there should be a categorical equivalence. And he proposed that if you have on the A model a symplectic manifold, and if you look at the Fukaya category of X, which is generated by Lagrangian submanifolds, then on the B model, there is on the mirror the bounded derived category of coherent sheaves, and Conjecture proposed that these two categories should be equivalent. And this is well known as the homological mirror symmetry conjecture. And the other important conjecture in mirror symmetry is a geometric conjecture, which is due to Strominger, Yau, and Sasso. And I will in a minute talk more about this. So the Gross-Siebert program is about algebro-geometric understanding of the Strominger-Yau-Sasso conjecture, which is formulated in the SYZ conjecture. I will tell it in very rough terms, omitting the structures here, but if you wish, please feel free to ask me questions. The SYZ conjecture is, in rough terms, proposing that if you have a Calabi Yau, then there is expected to be a torus vibration, a singular torus vibration on this Calabi Yau. And you can also construct a singular torus vibration on the mirror Calabi Yau. And these vibrations are expected to be dual to each other. So dual is in the sense that if you obtain one side from the tangent bundle modulo of the lattice, you look on the other side, the cotangent bundle, you quotient out with the cotangent bundle to obtain the torus fibers. And so these vibrations on Calabi Yau manifolds for topological reasons do need to have singularities, and the singular fibers occur over codimension 2 locus, which we call delta, which is called the discriminant locus. And away from delta, P minus delta carries the structure of an integral of one manifold, which means that you can find an atlas with transition functions in the semi-direct product of GL and Z with Zn. So this is a singular torus vibration. As choice, we always use red usually to denote the discriminant locus over which the singular fibers are. So I would like to tell that one natural setup where you can see torus vibrations is arising in the setup of toric geometry. Because if you look at the toric variety, it is an algebraic variety containing algebraic torus C star to n as a dense open subset, such that the action of the torus on itself extends to X. And these varieties can be constructed from combinatorial data given by momentum polytopes, moment cones. So the simplest example of a toric variety is P1, where I drew on the left-hand side of this picture here. And the momentum polytope for P1 is just the interval. It parameterizes the S1 fibers. There's a torus action given by rotation on the P1, which is we can visualize as usual two-sphere. And the momentum polytope parameterizes the orbits of this S1 action. And if you have a toric variety, you can imagine in rough terms that the mirror can be easily constructed, because the perception in mirror symmetry is that if you have a torus vibration, if your fibers are built of circles of radius r, then on the mirror side, you should replace them of circles with radius 1 over r. So if you see here a circle of radius r, you can replace it with a circle of radius 1 over r. And in naive terms, you can imagine the mirror of P1, actually P1 minus the north and south pole, as this C star here of this shape. So if you have a toric variety, mirror symmetry would be easier to approach. However, we want to understand mirror symmetry for Calabi Yau manifolds. So the question that is asked in the framework of the Gross-Siebert program is, can we find techniques to build Calabi Yau spaces out of combinatorial data using polytopes similar to the framework with toric geometry, similar to toric varieties? And the answer is yes. And the idea to do that is when you have a Calabi Yau, you can degenerate it into unions of toric varieties and build something that is not a singular toric variety, but a union of toric varieties glued along toric strata. And then you can construct the base of a vibration on the Calabi Yau by looking at each of the momentum cones of these components of the central fiber. And I will give examples of this. And by patching these momentum polytopes together. And then there are constructions on how to build a mirror Calabi Yau once you have this data on one side degenerating into toric varieties, and once you know what the base is, and once you know additional combinatorial data on the base, you can start with this combinatorial data and this degeneration and build a mirror Calabi Yau out of this data. And this is what Gross and Siebert do in their program. And the expectation is that on X, if you have a torus vibration, you can also construct a mirror vibration on this Calabi Yau, mirror Calabi Yau you build. So there are several constructions on how to build torus vibrations on Calabi Yaus as well as on mirrors. And depending on the level of interests, I mean, if you are looking for a construction where you only want to understand the topological vibration without caring about symplectic or complex structures, this construction was carried out in early on papers of Mark Gross, Topological Mirror Symmetry, where he explains when you give a polyhedral complex a polytope, and if you specify the discriminant locus, how you can build topological torus vibrations on such things. And this construction was generalized to the symplectic setup. The former students of Mark Gross, Riccardo Castano, Bernard Matessi, showed that the compactifications of Mark Gross, Calabi Yau compactifications, these are techniques to compactify smooth torus vibrations over the discriminant locus, can be carried out in the symplectic category. And there are other constructions, and most recently, we also, in our work with Siebert, showed that you can construct torus vibrations on families of Calabi Yaus using what we call Kato-Nakayama spaces, which I will also talk about. So I want to give an example of toric degenerations because we had mentioned the idea of understanding mirror symmetry for Calabi Yaus is to turn them into something similar to toric varieties. So the simplest example of a Calabi Yau family is the simplest example is a Tate curve, which is a family of elliptic curves, and it's a family of elliptic curves degenerating into chain of projective lines. So this is a two-dimensional Calabi Yau, and you can ask, we just thought we would be interested in six-dimensional Calabi Yaus. We actually are interested in any dimensional Calabi Yaus. So for several reasons, first there is some technical reason that arises in physics that some part of string theory is actually caring not only about the theory of T-duality, but you actually have mirror symmetry for all dimensional Calabi Yaus, and you can still do some predictions, and this is still interesting. But most interesting is six-dimensional, real six-dimensional ones, and we will come there too. So what I did in my PhD thesis, I investigated on the Tate curve, actually on the simplest case, and I showed that the two constructions, which I talked about early on in this setup, the homological mirror symmetry and the SYZ conjecture, I showed that they have several common features in homological mirror symmetry. You have several product structures, infinity structures. So this Conceivage is saying that the coordinate ring mirror to a Calabi Yau in this setup is given by the symplectic homology ring, and the symplectic homology ring has higher product structures. And I showed that these product structures can also be realized in this geometric construction. And I compared these two constructions for the Tate curve and showed that they're equivalent. So in rough terms, this means Tate curve satisfies homological mirror symmetry from the Gross-Siebert perspective. So the other interesting example of a family of Calabi Yaus are K3 surfaces. And I will tell you a degeneration of K3 surfaces, but I'm worried because I hear no one. Is it normal that I hear no one? Is everyone muted? Or is my computer muted?
No, everything is good. Everything is
good. Okay, perfect. If you look at a degree 4 homogeneous polynomial, then the zero set of this degree 4 homogeneous polynomial is a K3 surface. And you can look at the toric degeneration of K3 surfaces given by this equation that I wrote here. So x0, x1, x2, x3 plus t times f4 is 0 and p3 times a1. And if you look at the central fiber of this toric degeneration, it is given by a union of 4 copies of the projective 2 space. Whereas the general fiber is a K3 surface, being the zero set of a degree 4 homogeneous polynomial. And if you look at projective 2 space, toric geometry tells that the momentum polytope of a projective 2 space P2 is given by a triangle. So if you have 4 copies of these, they glue together to a tetrahedron that I drew here. And then you also, when you know the toric degeneration like this, you also know what the red dots, I drew here 24 red dots, which are denoting the discriminant locus. So the idea is you start with the Calabi Yau, you degenerate it, you associate the momentum polytope, and then you can understand the discriminant locus. You can label the discriminant locus, and then your Calabi Yau will admit a vibration over this momentum polytope associated to the central fiber, where there will be singular fibers over the discriminant locus. And the question is, how do you understand what the discriminant locus is from the toric degeneration? So we do that by endowing everything with sheaves and keeping track of where these sheaves behave well and where these sheaves don't behave well. And we call this log structures. So we do log geometry to understand if you're given a family, degeneration of Calabi Yau varieties on the base where we can label the codimension to discriminant locus. Okay, so I tried to draw a vibration of a K3 surface over this polytope and the mirror. So if you look at the K3 surface, it can be visualized as a torus vibration where over any generic point of this tetrahedron, you have 2 tori, and over any of these 24 singular points, you have pinched tori. And the dual looks similar. K3 is actually self-mirror. And if you go 1 dimension higher, if you come to the most interesting examples from the point of view of mirror symmetry, then we have the quintic threefold. If you look at a degree 5 polynomial in P4, This defines the quintic threefold. If you look at the zero set of x0, x1, x2, x3, x4 plus t times f5 equals 0 and p4 times a1. Then for t non-zero, you get a quintic, and for t0, you get a toric variety whose momentum polytopes are this time 5 copies of this tetrahedra, which is filled, which is homeomorphic to the tree sphere. And this is the base of a fibration on the quintic threefold. So I just drew one copy of these three spheres, which we drew as tetrahedra. So, and the discriminant locus is one-dimensional, which looks like this, which is given by a graph. And there are 4 more copies of such things which are mutually glued along each other. So I drew these small edges going out of here, which means that these small edges are actually edges that are part of the other tetrahedra. So this is one tetrahedra in the middle, and there are 4 more each glued along each other. And this is the base of the quintic threefold of a torus vibration on the quintic threefold we obtain. Okay, and the question is, the difficult question that I roughly mentioned is, how do I understand this discriminant locus? How do we draw this discriminant locus? And how do we understand the monodromy data around the discriminant locus, which is important if you want to understand how to construct vibrations, even on a topological level, on the mirrors? And the answer is given by log geometry. So we keep track of everything we need in terms of sheaves, and these are given by log structures. And this is the framework of log geometry. So a log structure, you can think of a log structure as a structure of pairs. And if you're in a degeneration situation, then there's a natural pair you can consider, given by the total space of the degeneration and the central fiber. And if you look at the total space, and if you consider the sheaf of regular functions on it with zeros on the central fiber, this is a log structure on the total space. And you can also pull it back to the central fiber, and you consider this sheaf on the central fiber, and this sheaf behaves well, namely it has a non-singular locus where you have this general fibers, and where this sheaf behaves badly, you get the discriminant locus of your fibration on the base of your Calabi Yau threefold. So the idea is you build a degeneration, you look at the central fiber, you endow it with a sheaf, and then you study the good and bad parts of the sheaf to determine the good and bad parts of your fibration on the Calabi Yau you want to construct. Okay, so, and we use all these log structures to construct Calabi Yaus and fibrations on these Calabi Yaus, and we do this by looking at Kato-Nakayama spaces. So once you have the log structures, you can describe a topological space associated to the log space with a log structure. This is called the Kato-Nakayama space. And its description is slightly technical, so I will not write it, but I will state what we had shown. If you have a toric degeneration of a Calabi Yau, then if you look at the central fiber together with this log structure that you can understand from this degeneration, then this is homeomorphic to tube. So there's a homeomorphism between the Kato-Nakayama space we construct and pi inverse of a small circle around the base. So there's a definition of a topological space using sheaves and log structures. And this description is, we showed that this definition gives you a tubular neighborhood around the central fiber of your degeneration. So you take a small circle S1 on your base and you look at pi inverse S1, and the Kato-Nakayama space is homeomorphic to this. And we studied topologies on Katonakama spaces in detail. We showed that they admit torus vibrations. We also studied involutions on them and the fixed point loci of these involutions. And so fixed point loci of anti-symplectic, anti-holomorphic involutions. And these are some nice Lagrangian submanifolds. And afterwards, in our work, which we had last year with Thomas Prince, we concluded several other things about the topology of real Lagrangian submanifolds and Calabi Yau treefolds. So one of our results was, for instance, if you look at the quintic treefold, then if you look at the real locus of an anti-symplectic involution in the quintic treefold, you obtain a real Lagrangian. And this Lagrangian is given by the disjoint union of the sphere, which is the base of your vibration, and another component which arises as a 7-to-1 cover over the space. And we showed that H1 is Z2 to 101. This is one of our results. I shall say that we deduced information about cohomology groups of real Lagrangians in a more general setup for Calabi Yau treefolds, not only for the quintic. So actually, maybe I can mention when we first wanted to understand multi-cohomology groups of real Lagrangians, which are interesting for various reasons.
I think there is a question.
Oh, okay. I cannot see the chat window somewhat. Sorry. Okay, if you might report me any questions, I really appreciate that.
Can you explain a little bit how the Kato Nakayama space relates to all the other spaces? I mean, yes, you say it's, how do you get the second bullet point? What's the relationship between X and Lagrangians inside X and involutions on the Kato Nakayama space?
That's a very good point, yes. So I was very vague here, I didn't write the details. So the thing is, the Kato Nakayama space is is only a topological space. So you can, I say involutions, they're real Lagrangians, so there are things I need to explain here. And that's a very good question, so I'm happy to explain them actually. So the data we need to construct the Kato Nakayama space is on B, on the base of the vibration, on the base B you obtain from your toric degeneration. You start with something called gluing data, and this gluing data is the same data which in the Gross-Siebert program they are using to construct smoothings of, okay, so let me say this. So if you're given
the B, do you mean the B with the singular points with the discriminant locus, or do you mean without the discriminant locus? Do you mean the singular integral affine space, or?
Singular integral affine space. So so the idea goes like this. You start with a toric degeneration. To the central fiber you associate B, which is an integral affine manifold with singularities. So you know what the singular affine space is. And you do know the singularities because when you're given the toric degeneration, on the total space there's a log structure, which is a sheaf of monoids, and you induces a log structure on the central fiber. And this log structure has some discrete part in it, which we call Gauss sheaves. So in this sheaf of monoids, there's always some part which is homeomorphic to the invertible elements of the structure sheaf, and if you quotient out, you get this discrete part called Gauss sheaf. And the log structure is nice if that Gauss sheaf can be written as natural numbers to the power, some copies of natural numbers. And it's not nice if it cannot, essentially. So when you have the toric degeneration, you know B together with the integral affine structure. And the integral affine structure is exactly the points where the log structure on X0 on the central fiber is not nice. So when you label the points where the log structure is not nice, from x0 there is a generalized momentum map to B, so assume and you label the images of these not nice points under the generalized momentum map. So when you have a Toric degeneration, you have the state of an integrally affine manifold with singularities. And now you want to build a smoothing of you want to build a family, mirror family out of this data. So this data of an integrally affine manifold with singularities is not enough to build a mirror family. Because first you need to build the dual central fiber. And in general, if you're giving me something like this, and if you tell you need to build the central fiber union of toric pieces, there are a lot of ways to glue these toric pieces. So if you have a P2 like this here, it's so if you have a triangle, you have one copy of P2, there is another copy of P2, but you first need to build the central fiber decide how to build the central fiber and tell how to smooth it. But you don't know how to build the central fiber out of this P already, because you don't know how to glue different toric pieces together. So the way you understand how to glue them is given by some additional data called gluing data on B. And this is telling you how the central fiber is glued. And once you know the gluing data, there's a unique way to smooth it given by some Gross-Siebert wall crossing algorithms. So once you fix B and the gluing data, we do know that there's a complex smoothing and the general fiber will carry a complex structure. And in our examples, we have shown that the Kato-Nakayama space is just homeomorphic to the smoothing of the family Gross-Siebert constructs. So we haven't investigated complex nor symplectic structures in my paper. So we only studied Kato-Nakayama spaces on a topological level. And we only showed that the Kato-Nakayama space is homeomorphic to the general fiber of a smoothing you can construct by using gluing data and wall crossing algorithms within the Gross-Siebert program. So the question is, what kind of involutions do you look at? So there's a result telling that.
Okay. So what kind of space is Kato-Nakayama space? Is it an algebraic variety? Is it what kind of space is it?
It is a topological space.
Just a topological space with no other?
It's a topological space, but we do know that it can carry we do know that it is projective. We do know that it's a projective variety in certain cases. And there's a characterization when we do know this and when these nice cases are true. So in mirror symmetry via log degeneration data part 1, they introduced Gross-Siebert introduced the gluing data, and they introduced something called projective gluing data. So if you initially start with projective gluing data to construct a Kato-Nakayama space, we know that it will be projective. It will be a nice variety which is projective. So it depends on what kind of gluing data you start with to investigate additional structures on these Kato-Nakayama spaces. So if you start with projective gluing data, you can embed the Kato-Nakayama space into a projective space. And that's a very good question. However, this is very technical to investigate this gluing data and explicitly understand the symplectic structures as well as the complex structures on Kato-Nakayama spaces. So that's why I didn't investigate this in my paper.
Yeah,
but
I mean, it seems like you were towards the end of your slides, so I thought.
Yes, that's a very good question. I really appreciate that you asked it. I actually lied a little bit by putting this Lagrangian into the upper theorem, because in our paper with Bernd, in my Kato-Nakayama paper, we never talk about Lagrangians. And the reason being we never talk about symplectic structures because it's very difficult to tell what explicitly the symplectic structure is. But we do know there exists a symplectic structure if you choose the gluing data nice enough. But the thing is, there is another construction which doesn't use Kato-Nakayama spaces, which is due to Mark Gross. He constructs torus vibrations on Calabi Yau manifolds starting from this B. So, and these two constructions are expected to agree with, and there's no proof yet to it. So if you start with an integral fine manifold with singularities P, there's an alternative construction which doesn't use Kato-Nakayama spaces. Just on a topological level, Mark Gross constructs torus vibrations once you fix the monodromy data. And the students show that these vibrations can be given a symplectic structure. And they describe the symplectic structure concretely, and they describe anti-symplectic involutions.
But this is only in 2 and 3 dimensions, right?
That's true, yes. The advantage of the Kato-Nakayama space, the Kato-Nakayama space construction works in any dimension, but the disadvantage is you cannot take very well control of symplectic structures. And the advantage of Mark Gross and his students' work is you can, in 2 and 3 dimensions, take control of the symplectic structures. Yes, you're absolutely right. And we investigated, that's why we took the toy models of Mark Gross's framework, and we took these vibrations, and that's why we could only investigate Lagrangians in Calabi Yau threefolds. If there could be a way that I could understand symplectic structures in Kato-Nakayama spaces, these Kato-Nakayama spaces come with maps to S1. I mean, there are expected to be symplectic structures if you restrict to a fiber to S1, which will be homeomorphic to the general fiber. If I could understand that, I could do that in all dimensions, but that's a challenging problem. So as you said, you're absolutely right. So in Mark Gross and students' work, it's restricted to 2 and 3 dimensions. And we investigated the topology of Lagrangians in these dimensions in detail using actually old work of Mark Gross. Yeah. That's a very good point.
Thank you.
Well, thank you very much for the question. That was a very good point. So, so actually what we did with Thomas is, a priori, in our first paper, we wrote a paper on real Lagrangians in the quintic threefold. And we just wanted to understand the topology in the quintic. And we really worked very hard to encode all the monodromy data we need to understand the topology and everything into Magma and Sage. So we wrote a code with thousands of lines. And we found all these results of these cohomology groups. But then, very nice referee, fair enough, thought that, why did you write thousands of lines of code just to deduce results about the quintic threefold? Can you not do a mathematical proof and bigger generality for Calabi Yau threefolds? And he made a conjecture for us, saying that you can actually capture the mode 2 cohomology of real Lagrangians by trying to relate them by a long exact sequence to Hodge numbers of the Calabi Yau. And if you understand the connecting homomorphism in this long exact sequence, you can capture all information you want, in particular the mode 2 cohomology groups of real Lagrangians. So we validated this conjecture of the referee and happily got our paper published for real Lagrangians and more generality in Calabi Yau threefolds afterwards. So, so this theorem I just stated for the quintic, but we showed this in much bigger generality with Thomas, and we wrote another paper this year showing how the mode 2 cohomology of real Lagrangians actually do connect to Hodge numbers. And the idea being the mode 2 cycles that generate the mode 2 cohomology groups of real Lagrangians are in correspondence with integral points in these polytopes, and these integral points, counts of these integral points were the work of Butirev, correspond to Hodge numbers. So that's how the mode 2 cohomology is related to Hodge number of the Lagrangians is related to Hodge numbers of the Calabi Yaus, and there are several interesting relationships in this context. So this, sorry, yeah. Was there a question?
I guess no question right now.
No question? Okay, so I'm almost about to finish. I had 2 more pages that I don't have a watch with me. How much time am I having left?
You have about 20 more minutes, so lots of
So we can have a lot of time for questions if you wish. I assumed 1 hour, but I went quick, probably. Sorry about that.
No worries.
So, okay, so if you want to understand a more challenging question, rather than, so the question we so far discussed was, so you have this B and you try to understand a way to construct vibrations, torus vibrations on Calabi Yau's, and either on a topological or symplectic level. But a more challenging question is, if you start with B, can you actually construct the homogeneous coordinate ring of a family of Calabi Yau's by starting with B? And this question is the main question that is answered in the Gross-Siebert program. You can do that, and to do that, what you need to use is a wall crossing algorithm on B. So this is a combinatorial algorithm that takes place on the integral affine manifold with singularities B. And I will talk about this algorithm in a lot of detail in 2 weeks. So if you're interested in the talk, Umut and Barish probably know their group on homological mirror symmetry is organizing some conference. So I didn't want to write all the details here because it will take at least another hour. I will be vague here. If you have questions, please do ask. So the wall crossing algorithm is an algorithm that is a technique to construct homogeneous coordinate rings of varieties. So if you have a toric variety, you know that when you have, as mentioned, a momentum polytope or a toric fan, like for P2, you have this toric fan with 3 regions. From each you can read the affine tube space A2, and you know how to patch them together to P2. But if you start with an integral affine manifold with singularities, you don't know a way to build affine spaces, and you don't know a way to how to patch them together. So the wall crossing algorithm is an algorithm to give a systematic way to do this, to telling you a systematic way to how to construct an affine cover and how to glue these pieces of affine cover together so that you obtain an algebraic variety at the end of the day. So to run this algorithm, you have an initial set of walls. These are codimension 1 sets which contain the discriminant locus on B, and then you systematically add more and more walls, more and more codimension 1 sets, and you add these. You do the systematic algorithm by looking at counts of curves on X. So these walls carry some functions, and which are going to tell you how to glue. So there are some chambers which are separated by the walls. These are going to correspond to your elements of your affine cover, spec of some things, and then on the walls you're going to have attached functions which are going to tell you how to glue together these elements. So the counts of curves are encoded in this algorithm in a combinatorial way, and for this you use tropical geometry. So if you want to do things combinatorially, and if you want to understand enumerative invariants also combinatorially that are included in this wall crossing algorithm, the main tool we use is looking for tropical curves into the appearing inside these wall crossing algorithms. And the main result in this construction due to Gross-Siebert is saying that if you have a 2-dimensional local Calabi variety, which is a variety obtained as the blow-up of a toric variety along points on its toric boundary, then the Gromov-Witten invariance of it can be computed algorithmically by wall crossing algorithms. So this was shown by Gross-Siebert, who showed that these wall crossing algorithms actually are very compatible with tropical geometry. So there is a systematic way where you add more and more and more walls by computing commutator groups purely algebraically, actually. And Gross-Siebert showed that this algebraic way to add these one-dimensional walls is actually not so random. At the end of the day, you always end up with balanced graphs. And I showed that these balanced graphs are really all of the tropical curves that give the invariance you want. So this count of tropical curves give Gromov-Witten invariance. And what we did with Mark Gross was to expand the result of Gross, and Siebert to higher dimensions. In our paper, which is on arXiv this year, we showed that if you have an n-dimensional log Calabi Yau variety, which is obtained as a blow-up of a toric variety along hypersurfaces in its toric boundary, then Gromov-Witten invariance of X can be captured algorithmically by wall crossing in higher dimensions. So we did wall crossings in higher dimensional bases and showed that you can still do tropical geometry and you can still algorithmically compute Gromov-Witten invariance out of these constructions. And there are words in parentheses that I was not planning to explain a lot, but in 2 dimensions you actually compute log Gromov-Witten invariance. And log means you're interested in a relative theory. It means you're looking at counts of curves with prescribed tangency conditions relative to some devices. And in higher dimensions, what you need is punctured log Gromov-Witten invariance, which means you're looking at, again, counts of curves with prescribed tangencies relative to some devices, but these tangencies can be negative, which means that, so you can imagine a curve having a positive tangency if it touches the divisor. And what it means negative tangency, it happens typically when an irreducible component of the curve totally falls into this divisor. Yeah, so I think this is all that I wanted to talk about today. Thank you very much for listening, for being here. If you have any questions, you're more than welcome.
Thank you very much, Hülya. That was a very good talk.
No, thank you.
Let's use reactions to clap. Is there any questions for Hülya today?
No. Sorry.
Any questions from the audience? If not, I have one question.
Oh, sorry. No, go ahead.
Soham, you can go ahead, please.
Hi, it was just more the codimension 2 subset in the singular fibers. Is there like intuitive reason why it's codimension 2 and not codimension 3?
That's a good question. So could there be a codimension 3 example in the So when you look at the discriminant locus, you're solving actually some set of equations, and you're looking at a singular set of some regular functions which happen to occur at codimension 2. Like in this case, if you solve this equals 0 and f4 equals 0, you obtain really 24 points. But it's a very good question if there could not be a higher dimensional singular locus, and if you have a smooth, if you have if your Calabi Yau is smooth, this is not happening unless you have some kind of orbifolds or I'm not even sure in that case. That's a good question. Yeah, I'm afraid I need to think about this.
That's okay. Thank you.
Thank you.
Thanks.
Thank you. Any other questions? Maybe while waiting for other questions, I can ask mine. You said in your thesis work, you looked at some higher multiplications coming from the homological side and showed that they can be realized in the geometric side. Did I get this correctly?
Yes, that's true.
Can you tell a little bit more about that and how those multiplication maps work in the geometric side?
That's a very good question. So, so this construction of Gross and Siebert proposed that you can algebra-geometrically construct this coordinate ring. But so far, there hasn't been a study of the product structures in this Gross-Siebert ring. So far, it hasn't been investigated if there is an A infinity or L infinity or whatever structure in this. And I did investigate this. So if only for the Tate curve, although in the physics literature, physicists expect in the B model there should be similar structures. But how does that work is, so the structure constants that contribute to the product on the A model on the symplectic side. So there's some products where you, okay, on the, I need to tell a little bit of bad terminology. So on the A model side, this product is on the symplectic cohomology ring, or in general in the Fukaya category, where you look at Lagrangians and the product is counting holomorphic disks bounded by these Lagrangians. Mm-hmm. And on the B model side, these holomorphic disks are expected to have algebra-geometric analogs by these things which we call log-Gromov-Witten invariants. Mm-hmm. And in the case of the Tate curve, I showed that these holomorphic disks can be counted from some tropical curves on the base of B. And using this tropical geometry, I went to the log invariants. So it's a very difficult question in general to relate the symplectic and algebraic Gromov-Witten type invariants. And there are very difficult constructions. I mean, there are virtual fundamental classes and very difficult to relate them, but the trick is, or the trick I used is to use tropical geometry in between to find a correspondence between these symplectic things and algebraic things with tropical geometry. So I just showed that for the Tate curve, it was known what these holomorphic disks are supposed to be. I just showed that they could be computed tropically, and then I used these tropical things to show that they can be computed algebra geometrically. And what I had shown is all these structure constants that you count in symplectic cohomology actually give rise to well-defined counts with log-Gromov-Witten invariants. And this expectation is conjecture in the paper of Gross and Siebert, saying that in the ring of theta functions, there's a product structure too. They write a product. And they don't work out A infinity structures in this product, but the expectation is the constants in this structure constants in this product are given by punctured log-Gromov-Witten invariants. And I showed that that is true for the case of the Tate curve, that these punctured log-Gromov-Witten invariants, counts of these actually correspond to counts of the holomorphic disks that appear on the symplectic side. So the main idea is just to use some tropical geometry on the base to relate the two symplectic and algebra geometric constructions.
Cool. Thank you.
Thank you very much for the question. Yeah, so I'm still thinking if you have a codimension 3 thing. So like, yeah, I need to, sorry, I don't want to probably say some things that might be wrong. Apologies for this. Who had asked this question? Maybe I can contact them later.
Soham.
Okay. Thank you for the question.
Actually, you can still talk because after this, Turkey will stop recording and we will have this informal coffee time.
Oh,
We will
perfect.
chat, so you can keep chatting if you want. So that is all for today, and we will just stop recording now with Turkey. And thank you.